Okay, good morning. So we were now on the next lecture, continue from the previous lecture. And this is lecture number. This is lecture number 17. 17, and today's date is 29/07/2021. And what is that we are going to discuss in this period is total crush energy. And we need to understand change in velocities, right? So these are the two titles that we are going to look at. So why do I put change in velocities is because you may be asked if you say I have learned Crashworthiness, or I can best explain crash event, you would be asked this question. So speed change of a vehicle is inversely proportional to, right? Let me write that statement and then we will prove that. Speed change of vehicle is inversely proportional to its mass. So what does that mean? That is, what does that mean? Heavier the vehicle, heavier the vehicle, smaller the change in speed. In speed, smaller the change in speed. So that is important statement coming out of this collision event to be proved now. So for that, let us understand total crush energy and whatever that so far we have been discussing. All are essentially to be in our mind when you go and prove this statement. Speed change of vehicle is inversely proportional to its mass. Similarly, you also have another statement when you look at an individual crush energy of the vehicle under collision. And what is that statement is the amount of crush energy is inverse to that of spring constant of structure involved in the crash event. So let's look at them now in this one period to understand. Right. So for that, what am I going to do is you may recollect in our lecture number 13 what we were doing. Lecture number 13, we were learned what is Kelvin's theorem for dissipated energy during collision. So you have to understand these terminologies very clearly. So when you say E equals ratio of relative velocity of separation by relative velocity of approach, you write, and that's what is defined by P by P dash. Right? If you have two vehicles A and B, I say that is VB dash minus VA dash by VA minus VB. If I say, you should say the numerator is what is P and denominator is what is P dash. Am I right? Sorry, this is just opposite. Just a minute. Relative velocity of separation is in the top and approach is here. So this is P dash by P. So we have this P dash is E times P. Like that we were writing it, you would remember. Now what is P and P dash you understood? That's there here. So the Kelvin's theorem states that dissipated energy during collision would be simply half the value of the product of the total external impulses present during collision multiplied by the addition of these two relative velocities. That's all. In that, if you look at further, you would be able to relate that the dissipated energy to the total crush energy. So what is total crush energy? What is total crush energy? If it is frontal barrier impact, if it is frontal barrier impact, the total crush energy is half into m into v square. So barrier is concrete and that mass is so huge, infinity if you consider. The vehicle mass m with the approach velocity of the vehicle or the impact velocity of vehicle is this, that goes and hits, and the total kinetic energy is what is the total crush energy. That's called total crush energy, not crush energy. And this total crush energy is absorbed by the structure during the interaction. That's what you understand. So this total crush energy absorbed by the structure during the interaction would dissipate energy. It's absorbed as well as it is not absorbed completely. It dissipates some energy and it is having some residual energy. So that residual energy is what is called a rebound energy. So the total crush energy minus dissipated energy is what is the residual energy, which is rebound energy. Right. So now, if this is the case of full frontal barrier impact, so one vehicle with the barrier, this. If I have two identical vehicle colliding head on head, just now we solved a problem. Then what would be my delta E to calculate is where we have introduced an effective mass equivalence in our lecture. And if we have that, you would be able to write this total crush energy as half into effective mass into P square. What is the effective mass here? If two vehicles colliding M1 and M2, then M1, M2 by M1 plus M2. And that is effective mass you can put. What is P here? P is the relative velocity V1 plus V2. Vectorially add. If they are head on head, then one will be opposite. If they are hitting one behind the other, then accordingly. So when I write the vector form here, you can write their direction and scalar way. You can have this p value and substitute that, and you get your total crush energy of two vehicle to vehicle head-on collision. Right. So this is what we have already seen and understood. So in this particular lecture, this Kelvin's theorem is what is finally used to get this. What is that? The dissipated energy is total crush energy into 1 minus E square. So this is what is proved during this 13th lecture. And for that we understood the concept of relative motion and relative motion during impact. So we were just having three cases, and this is what we are writing it here. You can once again see, and you see that there will be a common time at the crash time where you have a common velocity. So this p value would become 0 at one point and goes here like that. So p and p dash is always in opposite direction. That's why you have when you write E, you write it like this, right? You write it like this. In this fashion, you write it. So now VB dash minus VA, here VA minus VB. So that's opposite direction to account. And we were just proving that with the help of impulse and momentum equation 1 and 2. So before and after collision, we were writing for both the vehicle, and then we were more interested in getting what is this total impulse to prove Kelvin's theorem. We were proving that Kelvin's theorem here. And then we continued looking at proving delta E dash, the dissipated energy. So delta E dash is what is total crush energy dissipated, and that would be equal to delta E into 1 minus E square. So here it's very interesting. When E is 0, it's perfectly plastic impact, which is most preferred, but it is not possible. So that's why you get a very closer value of E during heavy collision is better always. So if you have like that, entire energy getting dissipated, so your crumple zone or frontal structure during interaction should take energy, absorb, and all the absorbed energy should be dissipated. Then there won't be energy, rebound energy that comes onto the vehicle. So that is what is ideal requirement that we have discussed this point on that day. Right? Yeah. And now I'm going to continue from this point what we discussed. And we were also seeing this on that days there is some confusion. There's no need of having such confusion. So delta V is V1 minus Vc. Delta V2 is Vc minus V2. Vc minus V2. Here I was writing it. That's Vc minus V2. Right? It can be vectorially. If I put vectorially, this all can be plus like that. And according to the direction of velocities, we can have it. So let's now, today's class, this all will be very clear now when I explain you. And we have these three. So here again, what are these three diagrams? Are representing direct central impact collision of two vehicles, the three cases. So vehicle directions before collision, same direction, and they collide because V1 is greater than V2, first case. Another one is head-on-head collision, the problem what we have seen now in our midterm examination. And the second case here is barrier. So V2 is barrier, you can say, or one vehicle is stationary, the other vehicle hits. Right? So these are the cases. So these cases can be solved clearly with the scalar equation itself because it is 1D motion. So one direction motion, vectorially writing equation not necessary. Straight away you can look at the direction of velocities and substitute them in consideration of momentum principle and definition of coefficient of restitution. So you would be able to solve for two unknowns with these two equations always. Right. So if you know the velocities after collision, you would be able to estimate the energy lost and so on. So what is important when our subject point of view, if we have head-on-head collision or any these two identical vehicle collision or two different mass vehicle collision, no problem. You have to take concept of effective mass. So ME equals M1 M2 by M1 plus M2. You have to take this, and E equals P dash by P. You have to take this. So these are the simplest way to look at and solve the problem, because you would get total E would be half into ME times P square, and delta E dash is delta E into 1 minus E square. So these are the equations readily you should remember and to solve problems. This all comes from Kelvin's theorem, what we have proved and solved till the last class on 13th lecture. So today's lecture I'm going to explain you the statement I made at the beginning that the speed change of the vehicle is inversely proportional to its mass. So how am I going to do? That's very simple. Just let's do that now, right? Any doubt in summarizing what we were doing in the last class and now? Do not have any doubt. So let me just proceed posting this scenario of collision is direct central impact. So direct central impact, the two head on head collision. So when I say head-on-head collision, direct central impact means you should understand it is 1D motion after before collision. And the center of mass, the vehicles are considered to be point masses and they are on the line of impact. So you have conservation of momentum holds along the line of impact. So this all are understood. So in today's discussion, this direct central impact of two vehicles with M1 mass and M2 mass, after the collision, it is perfectly plastic collision that I make understanding. So E would be 0 in this case. So then what would happen? Your delta E dash dissipated energy would be total crush energy, right? Total crush energy. So this is that case that I'm going to now take in my hand and solve to prove the statement I made in the beginning, right? So now, if that is so, let me just use these blocks to describe my vehicles. So rectangular box describing now the vehicle. So this is vehicle M1 and I have vehicle M2 and they approach each other and collide. And since E is 0, this is before collision, and after collision, what would happen? So let me consider my convention positive to the right, right? And after collision or at the crash event at maximum deformation phase, there is no restitution period. So when E is 0 means what? No restitution event. It's only deformation event and they embed together and then that would have a common velocity. Let's assume that velocity is direction VC and this is V1, this is V2, right? So this is M1, M2, two vehicle collision. So now let us understand how the velocities changes. For that, let me draw this vector diagram for velocities to understand. So V1 is now, say, assume that's greater velocity than V2, just to make that assumption. So this is V1, right? This is V1. And V2 is approaching and that is having smaller velocity. The length of this arrow represents the magnitude of this. So V2. So they are colliding each other. So this is that velocity vector. And then here it's a common velocity, which would be something, say VC here. So let me have this line as well. Now change in velocity is what? Change in velocity is this. Change in velocity is this. Delta. How do I define change in velocity? Is delta V1. So what is delta V1 is? Before and after collision, what is the change in vehicle 1 velocity? So it is V1 minus VC here. This is scalar way, right? Because the direction of V1 and VC is same. Here assume. So the difference comes. That is the change in V1 is this. Change in V2, second vehicle is what? Vehicle velocity. V2 is in this direction, VC is in this direction. After collision for the second vehicle, the direction reversed. That's what we see. It is coming here and then it is reversed. So it will be added. So it's going to be VC plus V2. VC minus of minus V2. So it's VC plus V2. So this is scalar equation. These two are scalar equation. If the other case, if I take these are different vector equation, I take accordingly, this will change. That's all. All right. So you have now this definition. So if I add these two, what I get delta V1 plus delta V2, I'll get VC goes off. It's V1 plus V2. So change in individual vehicle velocity, if I add, I get the sum of the two velocities. Okay. So now I know that the total crush energy of two colliding vehicle will be given by a half into ME into P square, right? Where this P is nothing but V closing velocity also it's called approach velocity or closing velocity. So I'll also put this as V close. So P is what is V close, right? So now what is ME? You know, it is M1, M2 by M1 plus M2. And you can rewrite this as M1 by 1 plus Rm, where Rm is M1 by M2 we have already defined. Or you can rewrite in terms of M2 by 1 plus Rm dash. So this is all we have seen in the previous class. I just write it so that you would recollect when you want to manipulate the equations. Right? So here what is Rm? So Rm is M1 by M2. Rm dash is M1, M2 by M1. So this is what is mass equivalence. So let's call these two equations, whatever that I have written, given by number. I'm going to write the number of the textbook so that it's easy for you to refer back, right? That's equation 7.26. And here I want to get this common velocity. So here in this delta V1 and delta V2. So I have to prove what ultimately this delta V1 by delta V2 is equal to M2 by. So I have to prove delta V1 by delta V2 is what is M2 by M1. So the heavier the vehicle, smaller the change in velocity is what is to say. This is to be proved. So for that, I'm just playing around with the known items so far in our class that we have seen, right? Um, so what is in this? I do not know. We see common velocity is what I do not know. I know approach velocities. So common velocities, how can I find out? Apply impulse and momentum principle and sorry, conservation of momentum principle. So that would be M1 V1. I'm writing scalar equation, vector equation addition, scalar equation I'm writing. So V1 is to the right positive. So M1 V1, M2 V2 minus M2 V2. So that's what is total momentum before collision. And after collision, they embed together and go because E is equal to 0. So M1 plus M2 with the common velocity Vc. So this gives me the velocity Vc as this M1 V1 minus M2 V2 by M1 plus M2. Right? So this is the common velocity expression. So let's call this equation as per the textbook, 7.25 it was. So now my task is what is to find out change in velocity. So change in velocity I would get delta V1 by the statement here from the vector diagram, that's V1 minus Vc. So substitute this Vc here, I would have V1 minus M1 V1 minus M2 V2 by M1 plus M2. So now taking LCM as M1 plus M2, M1 plus M2, I would have here M1 V1 plus M1 M2 V1 minus M1 V1 plus M2 V2 numerator. So M1 V1 minus M1 V1 goes off. So I have M2 common I can take out. I'll have M2 into V1 minus V2 divided by M1 plus M2, right? So now what is V1 minus V2? Am I right? Sorry, this is here. It is M2 V1 plus M2 V1. So this is plus. So what is V1 plus V2? V1 plus V2 is velocity of approach. That's P or V close velocity, closing velocity. So I can rewrite this here as M2 by M1 plus M2 into V close, closing velocity. Is what is delta V1. And I would also write it in this convenient form of definition of Rm. So if I divide this numerator and denominator by M2, what I will get? It's 1 by 1 plus M1 by M2, that's Rm into V close. Is what is delta V, right? And similarly, I can get my expression for delta V2. What was that expression? It is Vc minus V2. That's Vc plus V2. So Vc plus V2. Like I substituted Vc, I can substitute here and I can prove this finally to be 1 by 1 plus Rm dash into V close. So what is Rm dash? It's M2 by M1. What is Rm? It's M1 by M2, right? So these two equation set as per the textbook is equation number 7.27. So we have got now change in, yeah.
So we have a quiz at 9 a.m. Of
Yeah,
yourself.
yeah. Yeah, I just finishing it in 5 minutes. You can proceed. I'll finish it, right? 1 or 2
Okay, sir.
minutes.
Thank you.
Yeah. You have this change in velocities obtained now. So we just have to prove this change in velocities to inverse of their masses, right? Variation So how do I do that? I know now. On other hand, delta E will be by concept of equivalent mass ME into P square, that's equal to half ME into V close square. So I can get now V close as 2 into delta E by ME within bracket under square root. So now in this, so take this V close and put it in equation. So put in 7.27, I would be able to have my equation now. Delta V1 is going to be under root of 2 times delta E divided by ME. I just to substitute this in this, and I have 1 by Rm, right? So into 1 by 1 plus Rm. Similarly, I'll have delta V2 is under root of 2 delta E by ME into 1 by 1 plus Rm dash. So these are the set of equations 7.28. So now change in velocities calculated here. If I do take the ratio delta V1 by delta V2, what is that I will have here? See, I will have this. If I just you can do that simple, can be calculated from this, if you know crash energy. So you can find out this change in velocity. Now from this 7.28, what does that infer? I know Rm, vehicle mass ratios. Rm dash is the reverse of that. And ME I know. So vehicle mass I know. If I know total crush energy of the system, that is, if I know the velocity of approach, relative velocity of approach, I know what is change in velocity. I can just calculate. If I have this, and from this equation itself, I can prove this is going to be equal to M2 by M1. I leave it to you to prove that. And this is equation number 7.29. So in this, you just take this ratio, and that will end up with this. And what does that refer or convey? This equation is the speed change of vehicle is inversely proportional to its mass. This is M2 by M1, inversely proportional to its mass. So the heavier the vehicle, smaller the change in velocity. That's what is to be understood. I will stop at this point today's lecture, and we have smaller more discussion that we will continue in the next class on individual crush energy of the vehicle, and that is sufficient for central impact study. And what we have learned in the last lecture for non-central impact concepts of angular impulse and momentum principle and angular momentum conservation and so on. Let's use that for non-central collision problems in the next class, and that we will have tomorrow, Friday morning during lecture hour. So this afternoon, as I was telling, I may take a D1 slot. I will take in the next week, right? So there's no class this afternoon, and these are the 2 morning periods. On Wednesday we had 2 periods. This week, additionally, I take 1 period on Friday tomorrow morning, and then the remaining required classes I will compensate in the coming classes, coming week, right? And there would be a small change in timetable from the coming week. Monday A1 slot I will not be able to take, as we have another semester starts parallelly. I have a course allotted at that time, and now it's not easy to adjust in the timetable. So let's have in place of A1 slot, B1 slot from the next week for the remaining semester, right? So that's a note. I would stop at this point of time the lecture, and be ready for next week for your review of your J component. I would talk on that, what all, on when are we going to have scheduled tomorrow morning lecture, end of tomorrow morning lecture. Good day to all. Okay.